All right, so let me redo the recording for lecture 6 here, where we talked about the Broglie wave, electron diffraction spectrum, and Heisenberg uncertainty principle. I hope Dr. Kaufner took good care of you. So let's get started for the Broglie wave. So in this case, one of the idea of the Broglie wave is, since remember we introduced the wave-particle duality of light, or light can behave as a wave, right? The light can interfere with each other to create those diffraction patterns. At the same time, by the photoelectric experiment, we also identified that photons have wave-particle duality. So light also acts as a particle or little packets of energy with E photon equals to h mu. So the question now becomes, what if any other particles can also have wave-particle duality? So here's a quick review on the idea of standing wave. So imagine a guitar string where we have both ends fixed. And then you have a wave in there. And my drawing is not perfect, but you get the idea. They should have the same wavelength. And this is my third harmonic. We have two notes. And in any standing wave, the length, which is defined here, must be integer number of lambda over 2. So here, each distance here, that's lambda over 2. Here's another lambda over 2. All right, and n are integer numbers. So what we have here is a standing wave. Naturally, it's limited the wavelength any wave can take by fixing both ends. So now we came to the de Broglie's hypothesis. Right, what we have in de Broglie's hypothesis is that the quantization of energy in one electron system is associated with a circular standing wave that's oscillating about the nuclei. So here's a quick setup. You can imagine these are the wave associated with an electron in a one-electron atomic system. So in the de Broglie wave, again, we're considering it as a standing wave. So there are only certain amount of the wavelength are allowed. So what that means is the integer number times wavelength must equals to 2 pi r, which is the parameter of that circle, and equals to 1, 2, 3, etc. And r here is the atomic radii, or the radii. All right, so this is the equation 1 we're going to use in this quick derivation. And then we can use Bohr's hypothesis of angular momentum being quantized. So this comes to the Bohr model, one of his assumptions that angular momentum is quantized. So what we can have is that L, which is angular momentum, equals to n times, that's actually h over 2 pi. And in physics, we also know anything that's circulating with a circular motion, the angular momentum equals to m times velocity times the radii. Also in this case, n just any integer numbers. All right. So in this case, what we have is taking these two together, and apparently we have an r in my first equation. Let me rewrite my second equation. so that R equals to NH over 2 pi mv, and this mv just equals to the magnitude of linear momentum. Right, or we can have R equals to NH over 2 pi times linear momentum P. And combination, we have two expressions of R, and we can solve for lambda here. What we have is lambda equals to 2 pi R over N, and equals to, and here's where R comes from, 2 pi over N times NH 2 pi P, and we cancel out lots of the terms here, H over P. All right, and this is the expression of our de Broglie wave. I mean, the reality is a little bit more complicated than it, but for this course, this is as far as we're gonna go. So before we move on, I want to show you the full definition of wave-particle duality. What it states is that any particle, whether it's big or small, moving with magnitude of linear momentum p, will have wave-like properties. The Broglie wavelength of lambda is associated with the motion, and we have just solved for the de Broglie wavelength, which is lambda equals to h over p, where p is the magnitude of linear momentum here. H is a constant. So for any moving object, if we know its linear momentum, we know it's the Broglie wavelength. So let's look at one of the example questions here, right? So far we did lots of equation derivation. We're gonna do some practice here in how to use these equation derivation in solving a problem. So imagine you're asked to express the kinetic energy of an object in terms of its mass, the Broglie wavelength, and the Planck constant. So what we have here is that we know kinetic energy equals to 1/2 mv squared, right? So this is from basic physics. And then lambda, the Broglie wavelength, equals to h over p. We also know the linear momentum p equals to mv. Right, this also comes from basic physics. So what the question is asking is for kinetic energy. So we'll just do one big derivation and plug in. I have also the more stepwise approach in the annotated note if you like that approach better. So kinetic energy equals to 1/2 m times v squared. And from this expression here, we know that v equals to p over m. (1/2 m times p squared over m squared. And from this top equation, what we have is p equals to h over lambda. Then plug that in. Right, so let me just circle this. Right, I'm just taking all the m out. P equals to h squared over lambda squared. Let's cancel out one of the mass. What we have at the end is h squared over 2m lambda squared. All right. So it's just a quick derivation. What we're doing is moving terms, and you shouldn't be afraid of doing this type of question. Okay, now moving on. Before we talk about the spectroscopy, I want to quickly mention, we keep saying that the Bohr model only works for one electron systems. And why is it? So here's why. Now we know that electrons all have wave-like properties. Right, so all your electrons also have a de Broglie wave associated with it. What that means is your electron in atoms will also behave as waves. So that means your wave, your de Broglie wave of your electrons can also interfere with each other. In the Bohr model, in all our derivation, we're treating electrons as pure particle. And as a result of it, as a pure particle model, the Bohr model cannot address multi-electron systems because it cannot address the fact electrons are interfering with each other. All right, so that's just a quick note in why Bohr model is going to fail for multi-electron systems. And now we're moving on to talk about a quick application and also experimental validation of the de Broglie wave, which is the electron diffraction spectrum. We're just going to look at the experimental setup. We're not going into any math of the spectroscopy. You'll see that in physical chemistry courses. A quick background, the diffraction spectrum is not something new. People have been using the X-ray diffraction for years, or almost a century if not. What it means is when you have high energy X-ray, which is a light, it penetrates deeply into a single crystal solid. So when your light hits these nodes or these atoms in your crystal, what happened is a new beam of diffracted X-ray will be generated at each atom. Right? So the red line here are the incident X-ray, and the blue line here are the diffracted X-ray. All right. So the result here is whenever the spacing between these successive atomic scattering centers are comparable to the lambda of X-rays, they will interfere each other to generate the diffraction pattern. So in the reality, what we have, I mean, we used to just draw it as a line, right? But we know they're light. So they behave like plain light wave. So again, on the left, we can have incident X-ray. And on the right, we have the diffracted X-ray. And when the spacing and the lambda are comparable, when I say comparable, if you see, say, spacing is 200 nanometer, the wavelength we use is 180 nanometer. So that is comparable. In comparison, if my spacing is 200 nanometer and my wavelength is like go extreme, like 20 nanometer, so that's not comparable. Right, so in my questions, I'll make it clear whether it's comparable or not. And when these numbers are comparable, the incident X-ray and the diffracted X-ray are going to create something called a diffraction pattern. All right. So, quick example in what the X-ray diffraction has been used is to determine the structure of the complicated molecules, for example, like DNA, proteins, new materials. On the right, I'm just showing one of the most famous X-ray diffraction pattern, which gives you information that your DNA is a double helix. All right, so that's a quick review on, well, maybe not a review for you, but a quick introduction to the X-ray diffraction pattern. Now we're ready to talk about electronic diffraction spectrum. Or the reason I say it's a validation of the de Broglie postulate is the following. If electrons also have wave-like properties, what do we expect? Right, so we would expect a diffraction pattern if the de Broglie wavelengths which is given by lambda equals to h over p is comparable with crystal separation. So here's a experimental setup. What we have is that instead of X-ray, which we use light as the source wave, now imagine a beam of electrons was directed towards a crystal sample. All right, so that's my electron gun. And electrons with certain kinetic energy. Remember what we did? Once you have the kinetic energy of these electrons, you can translate it back to the de Broglie wave. You can do that calculation and get an idea about what the de Broglie wave of your electrons are. And the speed or kinetic energy of the electrons can be varied to change their de Broglie wavelengths. And once your de Broglie wavelengths of the electrons and the crystal splitting are comparable with each other, we can get electron diffraction pattern. And this diffraction pattern gives us an experimental validation on the wave-like behavior for electrons. All right. Now moving on to the third topic of today, which is indeterminacy and uncertainty. What we already know here is we talked about the wave-particle duality. One of the consequences of the wave-particle duality is that there doesn't exist anything as a pure wave, nor a pure particle. One of the clear consequences of particles have wave-like character is we know the position of the wave is not very well defined. Right, you can imagine a traveling wave, and it's like going like this in space. Right. So how can we tell where exactly is that wave in space? So that's not well defined. And that's why we have the Heisenberg uncertainty principle. So here what it means is when we measure two properties A and B together, we will obtain a spread in the result that satisfies the following equation. We're talking about any random property A and B, and the spread in A and spread in B. So these sigma are the spread in the result. You can roughly estimate it as, you can roughly pair it with like standard deviation, just not that accurate. It's larger than or equal to h over 4 pi. And in this case, sigma A and sigma B have the same units as A and B. And again, we know that unit tells us lots of information. In this case, we know that h is on the right-hand side of this relationship. So we can deduct what can be these physical properties A and B. So there are two major pairs of the physical properties that cannot be measured together with indefinite accuracy. So let me just copy my Planck constant down here. Right, so either it's joule second or kilogram meter second. So the first pair here is position, which has units in meter, and momentum. Whether it's a linear momentum or angular momentum, the unit of momentum is always kilogram meter second. All right, so that's the first pair. And this is what we're going to be focusing on for this lecture. And a quick note, we have a second pair that cannot be measured together with indefinite accuracy, or infinite accuracy, I'm sorry, which is time, unit of S, and energy, which is in joule. So this is why we keep, well, one of the reasons we keep emphasizing unit is that unit can tell us a lot of information, and it's going to be your friend when you're working on the exam questions. So let's look at one quick example. Let's look at some example and see how does the Heisenberg uncertainty principle, again, we don't see it in our daily life, but we do observe it in the microscopic world. So I'm going to show you two examples here. The first example is the macroscopic world, right? We have a moving tennis ball that is moving at the speed, which is a world record speed of 263 kilometers per hour. The mass of tennis ball is likely to be 55 grams, more or less, and a beam of laser is used to determine the position of the ball. And the question is, can you calculate the minimum spread in the speed of this tennis ball? And it's also given that approximately sigma x, which is the spread when we're measuring the position of the tennis ball, is roughly equals to the wavelength of the laser used to measure it. So how do we approach the problem? One of the things I like to do is always just write down what are the things that's needed to solve this problem, right? So for example, the sigma x, sigma p is larger than or equals to h over 4 pi, so that's our Heisenberg uncertainty principle. P equals to mv, that's our basic physics. Sigma x is roughly equals to lambda, that's given. And we also have a Planck constant. So these are all the information we need to solve this problem. All right. So in this case, let's start by looking at the question. It is asking for the minimum spread in velocity, right? So because we're asking for velocity, we can first have velocity equals to P over M, or sigma velocity, the spreading velocity. That's the same idea as sigma P over M. Plug that in to the Heisenberg uncertainty principle. We have sigma P is going to be larger than or equal to H over 4 pi sigma x. This is just moving terms around in the Heisenberg uncertainty principle. We know sigma x is a positive number, and that's why we can move it around. So taken together, what we have is sigma b is going to be larger than or equal to H over 4 pi sigma x mass, which we know this time mass of the tennis ball. And then plug in the numbers. We have sigma x roughly equals to lambda. We have the mass of the tennis ball equals to 55.0 gram. And we're talking about the minimum, right? So it's larger than or equal to. So sigma b minimum equals to H over 4 pi sigma x mt. We know H is a constant, 4 pi is constant. Sigma x, plug it in here, and mt, plug it in here. And do that calculation, you get sigma b is roughly equals to 1.48 times 10 to the negative 27 meter per second. And we can compare it with the speed of the tennis ball. So we have Vt, velocity of the tennis ball, is 263 kilometer per hour, or translated into a meter per second, that's about 4.38 times 10 to the negative 27 meter per second. And we have our calculated indeterminacy, sigma b is roughly equals to 1.48 times 10 to the negative 27 meter per second. I'm sorry, I have this one. So that's not such a small number. Right, so we compare these two numbers. And we can say the sigma b here is negligible. The other way is you can deduct the de Broglie wave of the tennis ball and see if it's going to interfere with the laser we use to measure the speed, or what we call a wave perspective. Let's say, so that the de Broglie wavelength of the tennis ball we have lambda t equals to h over p. Right, p stands for tennis ball, which is h over mass of the tennis ball times velocity of the tennis ball. We have all the numbers and plugged in, do the calculation. You get that to be 2.75 times 10 to the negative 36 meters. So again, my lambda t is not comparable with lambda, which is the laser we use. Or if you think about it, right, you have, let me just take it to the extreme. You have two waves. One of them has a very, very, very small wavelength. So we're talking about something like this. Right, so that's our super small wavelength, lambda t. So this lambda, which is the laser, that's like 650 nanometer. So that's a big wavelength comparing to what we have. Imagine a big, big wave. All right, so the effect of, so the interference will have minimal effect between each other. Or on the graphical representation, what we mean is that, say, the blue one is a tennis ball trajectory, and the red one is a laser beam. And if you think about that tennis ball, right, we calculated its wavelength, lambda t, is 2.75 times 10 to the negative 36 meter. And here we have the laser beam. So because these wavelengths are so different from each other, there is negligible perturbation of the trajectory of the moving tennis ball. You can do these calculations yourself. So now imagine we have a beam of electron that moves in vacuum with a much faster speed. Again, we use a beam of laser trying to determine the position of a specific electron. And you can calculate the minimum spread in the speed of this electron. So I'm going to skip all the calculation just to show you the graphic representation. You can see the deviation results in the annotated notes. So let's go all the way down to the wave perspective, which we can quickly do. The first part you can also calculate. So lambda E, which E stands for electron, equals to h over p linear momentum of the electron. So that's h over mass of an electron and velocity of an electron. Do that calculation, you get that to be about 36.4 nanometer. And we see that this one is pretty comparable to lambda, which is 520 nanometer. Or at least it is not negligible. This is different from the crystal spacing negligible problem we're talking about. So if you draw it out, what you expect is something like this. The blue one is still a small wavelength, but it's relatively comparable to the lambda of the laser beam. So here we might have interference that change the trajectory of the moving electron. All right, and the graphical representation, if we have it, let's imagine this is the electron trajectory. If there's no interference. All right, we have an electron here where we take the measurements with a laser beam. Lambda equals to 520 nanometer. So what happens is the trajectory of the electron will be perturbed. And this indeterminacy not ignored. All right, Here is my quick recording for the de Broglie wave and the Heisenberg uncertainty.